Communication models are fundamental to agent interaction in distributed systems, shaping how messages are exchanged and processed. Two primary models, synchronous and asynchronous messaging, each offer distinct trade-offs in responsiveness, scalability, and system resilience. Synchronous messaging resembles a phone call. Both sender and receiver must be available simultaneously for communication to occur. This model ensures immediate feedback, making it suitable for time-sensitive interactions such as confirmations, queries, or real-time data exchange. However, it ties up system resources while awaiting responses and may reduce efficiency under high load or network latency. In contrast, asynchronous messaging functions like email. Messages are sent and queued, allowing the sender and receiver to operate independently. This decoupling enhances scalability, supports fault tolerance, and is well suited for distributed environments where agents may experience intermittent availability or varied response times. Choosing between these models or combining them depends on system requirements, including timing constraints, communication reliability, and load handling capabilities. Effective implementation of these models enables robust, flexible, and efficient multi-agent communication. In agent communication, the choice between synchronous and asynchronous messaging significantly impacts system responsiveness and scalability. Synchronous messaging requires both the sender and receiver to be available at the same time, much like a phone call. The sender waits for an immediate response before proceeding. This model is vital for tasks that demand real-time feedback, such as transaction confirmations, critical updates, or time-sensitive decisions. While it ensures quick resolution, it can also tie up system resources and reduce efficiency under heavy loads or high latency. Asynchronous messaging, by contrast, resembles sending an email. The sender dispatches a message and continues its process without waiting for a reply. This decouples agents, promoting greater scalability and resilience, particularly in environments where network reliability varies or agents operate intermittently. Understanding when to use each model or how to combine them is essential for designing robust and efficient agent-based systems, especially in distributed or high-throughput scenarios. The request-response pattern is a fundamental synchronous communication model used in agent-based systems. In this pattern, an agent sends a request to another agent and waits for a response before proceeding, similar to placing an order and awaiting confirmation. This interaction ensures acknowledgement of the request, enabling agents to confirm receipt, verify outcomes, and handle errors systematically. This pattern is especially useful in scenarios where reliable transaction confirmation is essential, such as querying information, initiating services, or executing coordinated tasks. It promotes clarity and accountability between communicating agents by establishing a direct and time-bound communication loop. However, the request-response model can introduce latency or blocking, especially if the receiving agent is delayed or unavailable. This can affect overall system responsiveness, particularly under high load or in distributed environments with variable connectivity. Despite this limitation, the pattern remains widely used in application programming interface, API, calls, client-server interactions, and transactional workflows where immediate validation and structured error handling are critical. The publish-subscribe pattern is an asynchronous communication model that enables agents to exchange information without direct, predefined connections. In this pattern, publishers send messages to a central channel or topic without specifying recipients, while subscribers register interest in those topics and automatically receive relevant updates. This design promotes significant decoupling between senders and receivers. Publishers are unaware of who the subscribers are, and subscribers do not need to know the identity or status of the publishers. This supports many-to-many communication, enhancing modularity, scalability, and flexibility in distributed systems. The pattern is particularly effective in event-driven architectures, real-time monitoring, and dynamic notification systems, where multiple agents must react to system changes, environmental conditions, or broadcast updates. It allows systems to evolve with minimal reconfiguration, as new agents can subscribe or publish without disrupting existing flows. By promoting loose coupling and asynchronous delivery, the publish-subscribe pattern enables robust, scalable communication in complex multi-agent environments. The broadcast pattern involves sending a message to all agents within a system simultaneously, akin to a public announcement in a shared space. This model is particularly useful for delivering system-wide alerts, configuration updates, or critical notifications that must reach every agent regardless of individual roles or states. Broadcasting offers the advantage of immediate universal dissemination, making it ideal for use cases such as emergency alerts, synchronization signals, or global state changes in distributed agent networks. However, this pattern also presents notable limitations. Since messages are sent indiscriminately to all agents, it can result in unnecessary bandwidth consumption, especially when many recipients do not require the information. Additionally, the broadcast model lacks built-in feedback or acknowledgement mechanisms, making it harder to confirm message receipt or handle individual responses. Due to its efficiency in reach but lack of precision, the broadcast pattern is best reserved for scenarios where urgency and breadth outweigh the need for targeted delivery or response tracking. Message timing plays a critical role in shaping how agents interact within a distributed system. In synchronous communication, the sender must wait for a response before proceeding, ensuring immediate feedback but potentially causing delays if the receiver is unavailable. This model is ideal for interactions that require confirmation, such as in transactional workflows. In contrast, asynchronous communication allows the sender to continue processing without waiting for a reply. This promotes independent execution, enhances system responsiveness, and supports scalability in environments where agents may operate at different speeds or availability levels. Choosing the right communication pattern is essential. Use request response for direct, time-sensitive interactions requiring immediate acknowledgement. Use publish subscribe to share updates with multiple agents efficiently and without tight coupling. Use broadcast for wide-reaching alerts or global system notifications. Understanding these timing models helps ensure that agent communication is both effective and efficient. In the next section, we'll explore the security and trust mechanisms necessary to protect these interactions and maintain reliable, secure agent collaboration.